Alright, so here in our first question, we are attempting to predict the products of a series of organic reactions. As we've seen questions like this many times before, we know that the first, what we really want to be able to start with is by determining, what is the reaction that's taking place. And so this first one, question 1A, we have an electrophilic aromatic substitution reaction. But in a case where the aromatic ring is already substituted. So we know that this is not only an aromatic substitution, but specifically a bromination. And so what we need to determine is the thiol group. Is that an ortho-para director or is it a meta-director? Thiols have equal electronegativity with carbon, and with the lone pair, they are definitely electron donating groups. That means that they are ortho-para directors, and therefore we will see both products where we get the bromine ortho to the thiol group as well as para. Part B, we have a Grignard addition to a conjugated carbonyl. Now, what's the determining factor for whether we get 1,2 or 1,4 addition? The determining factor is our nucleophile a sufficiently good leaving group? And we know that Grignard reagents, or carbanions in general, are terrible leaving groups. So this will add 1,2 and then not go any further. Part C is a sulfonylation. We don't need to worry about the position it goes on because the ring is not substituted to begin with. So we get that product. Part D, when we see this triphenylphosphine reagent, we know we're probably looking at a Wittig reaction. But Wittig reactions normally require ketones or aldehydes. What we have here is an ester, and so therefore this reaction is not going to work. Part E is the reaction of an acid chloride with a carboxylic acid. Hopefully we recall that this is a good way to make anhydrides. Where the carboxylic acid functions as the nucleophile and the acid chloride is our electrophile. Part F, we have a compound that clearly can form an enolate in our ketone, and we have another compound, this conjugated aldehyde, that can't form an enolate. So given the one double bond here that's conjugated into the aldehyde, this is going to be a conjugated addition of the enolate, or a Michael reaction. To give us this product. Part G here, we have a good leaving group with the tosylate group. We also have a strong base under protic conditions with protic solvent, so this is an E1 type elimination. Being a secondary leaving group, those certainly can function under E1 conditions, and we will get elimination to form cyclohexene. All right, part H is the addition of an amine to an aldehyde, but this one is conjugated as well, and amines, we recall, are sufficiently good leaving groups that we can get a 1,4 addition here. Part I is an alkylation. We're using the strong base LDA to make an enolate. Given the strong base and low temperature, we are going to form the kinetic enolate, and so the methyl group will go on the less substituted carbon. J is a Williamson ether synthesis. K is the ring opening of an epoxide. Now remember that this reaction has some variation depending on whether we're under acidic or basic conditions. Under acidic conditions, it behaves more like a carbocation. Under basic conditions, it will go to the less substituted position. HCN, while not the strongest acid, is still an acid, and we should expect to see that the nucleophilic attack will happen at the more substituted carbon. And then finally, for this first question on part L, we have one of our amine synthesis reactions. Where first the deprotonated nitrogen does an SN2 reaction onto the alkyl halide, and then with the addition of base, or additional equivalents of base, we cleave the amide bonds to form the primary amine.